Good morning, class. We are looking at statistics, practice test number 2, covering module 2, chapters 4 and 5. Here's chapter 5, discrete probability distributions. Chapter 5, discrete probability distributions. That's what we are covering today. So we are covering chapter 5. Does the table describe probability distribution? What is the random variable? What are its possible values, and are its values numerical? So as we look at the table, number of gears in 3 bits, x is the number of gears, 0, 1, 2, 3, and p of x, the probability are as follows: 0.125, 0.375, 0.375, 0.125. So does this represent a probability distribution? Let's look at the concept. Number one, the variable x, which is the number of gears in 3 bits, 0, 1, 2, 3, is a numerical random variable. So it has to be a number, so it is. Its value describes probability. The value must be describing probability. Number two, some of the probabilities, if we add them up, they must always add up to 1. So when we add up the numbers in the second column, which is p of x, they will add up to 1. So far, so good. By the way, the only time it may not, if it has been rounded, if it's extremely close to 1, that is acceptable, like 0.9999, many nines, or 1.0000 and then 1. That is due to round up error, and that's okay. Each value of p of x must be between 0 and 1. So probability can't be negative, can't be larger than 1. And all of those 3 conditions work out for this table. Therefore, it is a probability distribution, everybody. In a game, you pay 60 cents to select a 4-digit number. If you win by selecting the correct 4-digit number, you collect $3,000. How many different selections are possible? Well, there are no restrictions. N is the number of digits. From 0 to 9, we have 10 of those. So there are 10 possibilities in 4 spots because it's a 4-digit. So simply 10 to the power of 4 or 10,000. Of course, numbers can repeat because there is no restriction. We just are looking for a 4-digit. What is the probability of winning? By definition, probability of winning is n of winning over n of s. So this is n of s, everybody. And there's only one way to win, so 1 over 10,000. If you win, what is your net profit? Well, you win $3,000, but you spent 60 cents, the difference. So net profit would be money gained minus the investment or the cost. So 3,000 minus 0.6 makes it $2,999.40. Write the probability distribution of net profit. So we make up the following table. Number of the net gain is x. P of x is the number divided by total, $3,000 for the winner, losers, total. So number of how many winners will we have? In this case, there's only one, and the rest of them will lose. If the total is 10,000 and one goes here, the rest of it, that means 10,000 minus 1 goes here, the total is 10,000. So total is 10,000. There's one winner, and the rest of them, 9,999, will not win. So For the winner, the net gain or X or net profit is this much, right? In other words, 3,000 minus 0.6. But for those who didn't win, the net profit would be negative 0.6. So I hope everybody's following that. This is the probability distribution. Now, what is the probability for this one is 1 over 10,000. For this one is this number, 9,999 over 10,000. This is called probability distribution of net profit. Very straightforward. So that's the table. This is from the previous page. Now, we are continuing with the question. The next part is asking, okay, now what happens? Find the expected value and interpret. Now, the expected value has this formula, mu, or the expected value is summation of x times p of x. So this is the x column. This is the probability or p of x column. So according to this formula, multiply these two, and then multiply these two. So x p of x, we're going to get to that in a moment. But what is x p of x? Multiply these two columns. This times this times this. So when we multiply these two, we get 0.29994. When we multiply these two, we get negative 0.59994. And summation of x p of x, add these two. So add the column, add these two numbers. We put it here, and this is the average. Therefore, the answer to part E, mu, which is summation of x p of x, is negative 0.3. So why did we make up this column? This is the easy methodology of calculating the value of mu. So it's pretty straightforward. Now, the next part is to find x squared p of x, because we want to find sigma squared and then sigma. Sigma squared is the variance, and sigma is the standard deviation for the population. It's important to always write formulas, everybody. So what is x squared p of x? X squared, raise this to the second power, and then multiply by this column. So raise this number to the second power, multiply by this, you get this one. Raise this to the second power, that actually becomes positive 0.36, because it's 0.6 times 0.6. Multiplied by this number, put it here. And now, summation of that, add those two values. And the reason we are doing, because we want to find sigma. Now, we use sigma squared to get to sigma. Sigma is the square root of this. You can use this formula or this formula. Summation of x squared p of x, we have it as this number, minus mu squared. So we're going to use this formula, everybody. That's the formula. You have it in your formula sheet. Sigma squared is the variance. We want sigma, the standard deviation. So we take a root of this expression. X squared p of x is 900 minus mu is negative 0.3 quantity squared. And take this to the power of 2, subtract it from 900, take a root, and you get 29.9985, almost $30. So the reason we calculated this is because of this one. What is the interpretation? The average is negative 0.3. The standard deviation is about $30. So on average, all players, a player loses $0.3. That means 30 cents per ticket, with standard deviation of $30. So on average, everybody gains this much, this happened to be negative, that means everybody loses this much. Okay, that's the concept that is important to understand. So in other words, negative means it's positive for the house. In this case, those who are giving you the game or offering you the game or offering the tickets to be bought. A pharmaceutical company receives large shipments of aspirin tablets. The acceptance sampling plan is to randomly select and test 24 tablets. The entire shipment is accepted if at most 2 tablets do not meet the required specifications. If a particular shipment of thousands of aspirin tablets actually has a 5% rate of defects, what is the probability that this whole shipment will be accepted? So notice we are dealing with what's called a binomial, BD for short, binomial distribution. N is 24, probability of defect is 5%. Why is it binomial distribution? The shortest explanation is that there are 2 outcomes. When you pick a tablet, there are 2 possibilities. It is defective or not. That's the idea. So, and here's the formula. P of x is, this is CNX, the combination of n choose x, n factorial over x factorial times n minus x factorial. P to the power of x, q to the power of n minus x, mu is np sigma is square root of npq, and q is the complementary event, 1 minus p. So that is the formula. So what is a binomial experiment and PD probability distribution properties? Number one, we have n identical or fixed number of trials. Each repetition of the experiment. Each has 2 categories, 2 outcomes. Yes, no, good, bad, defective, non-defective, things of that nature. Probability stays constant. So from one tablet to the next, the probability doesn't change. And they're all independent trials. So with that being the case, if I want to put this into this formula in general, I'm going to replace the n with 24 and p with 0.05. And of course, q must be 1 minus that. So this is p of x. 1 minus that would be 0.95. Plug in. When we plug in, we get 24 factorial over x factorial times 24 minus x factorial times 0.05 to the power of x times 0.95 to the power of 24 minus x. It's important to understand formulas and know how to use them. The entire shipment is accepted if at most 2 tablets do not meet the required specs. Probability of x less than or equal to 2. That means when x is 0, when x is 1, and when x is 2, we are going to add them up. That's the meaning of it. And it's 0.8841. How do we get that? I want to make sure everybody's clear as to how we get that. Into this formula, you plug in 0, gives you a number. Then you plug in 1, gives you a number. And you plug in 2, gives you a number. Replace the x with 0, 1, 2, and then add them up. That's how we arrive at it. Now, if you write the formula, if you write P and Q and you write this one and you write this one, and now you want to use a calculator, it's absolutely fine. But complete justification is here. And after this one, Now this number comes from a calculator as follows. To use a binomial distribution, second variables, binomial PDF, enter NPX and enter. If you enter NP only, gives all probabilities from 0 to n. If you use binomial CDF, cumulative distribution, and then it adds them up, gives the sum of the probabilities from 0 to x, and that's what we want to use because we want to go from 0 to 2, probability of x less than or equal to 2. And so binomial CDF trials, how many? N 24. What is the probability? 0.05. It is called the probability of success. Success doesn't mean positive or negative. It's just the probability of what we are interested in. Okay. And so 0.05. What is the x value to? So it gives you this number. And that's what we have here. And of course, this has a lot more decimals, as you can see. It is known that 70% of managers of all companies suffer from job-related stress. What is the probability that in a sample of 20 managers, exactly 8 suffer from job-related stress? So what do we have here? Binomial distribution. Why is that? There are two outcomes. Either the managers suffer or do not suffer from stress. So it's a binomial distribution. We are dealing with 20, that's a sample of 20, n, and the probability of success is called, again, doesn't mean anything. P is 0.7. So using the binomial distribution formula, P is a 0.7, Q is 1 minus that 0.3, and we can put it into this formula, everybody, replacing N with 20, P with 0.7, Q with 0.3. And now for part A, we want X to be what? 8. Simply put, you want P of 8. Replace the X with 8. So notice everything remains, okay? X is replaced by 8. 20 minus 8 is 12. So now you have that. You put it into a calculator if you want. So binomial PDF now. Why PDF? You just want one piece. One piece. It's PDF. 20 P is 0.7. X value is 8. And that's the number that you have with a bunch of decimals. Again, as far as the decimals class, just see how many decimals they ask you to come up with, and you follow it accordingly. Always follow that accordingly. We're going to continue with the same question, part B. At most, 8 suffer from job-related stress. So simply put, probability of x less than or equal to 8, which means probability of x equals 0, 1, 2, 3, all the way to 8, which means add them up. So you're explaining to your reader, you need to find P of 0. And remember this, everything that you have here is from the previous page. You have to calculate probability of 0. That means replace the x with 0 here. Then you have to calculate probability of 1, replace the x with 1, all the way to 8, replace with 8, add them up. You are telling your reader exactly what you need to do. And at this point, you can put it into a calculator. So first, justify your steps for the reader. So binomial CDF, because you're adding them up. N is 20, P is 0.7 or 0.7, X value is 8, and this is the number. If you stop at this point, it's 8. If you stop at this point, next to it is 6, you take it up to 2. Now, at least 9 suffer from job-related stress. Well, probability of x larger than or equal to 9 means calculate the probability of x at equals 9, 10, all the way to 20. And you can do that and you add them, okay? However, and that's fine, you should recognize this is the same as 1 minus probability of x less than or equal to 8. I hope you recognize those, okay? Because probability of x larger than or equal to 9 and probability of x less than or equal to 8, they are complementary events. They add up to 1. These two values, they add up to 1. So this is 1 minus that. And we already have calculated this in the previous step right here. And I'm going to write, if I stop here, class, number 3 next to it is 8, we change it to 4. So I'm going with a little bit less decimal. Again, the number of decimals, you have to pay attention to what they ask you, and you get 0.99486. So at least 9 are suffering from job-related stress. That has a very high chance of well over 90%, 99%. So that's important to understand. We are looking at the same question. This is the information from the previous page, part D. Find the expected value. Mu or E of X is NP. Again, the given that you have from the previous page, N times P, the product of these two numbers, and that is 14. So what it means is, if we know 70% suffer from job-related stress and we have 20 of them, the product of the two, we expect 14 to be suffering from that. That's the meaning of the expected value, the average in essence. Find the standard deviation. Sigma is square root of NPQ. So sigma squared is NPQ. So this number times Q, which is 4.2. And sigma is the square root of this number. And this has 1 decimal, we go with 2 decimals. As far as the number here, again, you got to pay attention to what they say. If they don't mention the number of decimals, then you have to use many, many, many decimals. Would it be unusual to claim that 7 managers from this sample suffer from job-related stress? So I hope you remember that mu plus minus 2 sigma represents usual beyond the two numbers. That means mu minus 2 sigma less than that is unusual. Mu plus 2 sigma larger than that number is unusual. So mu minus 2 sigma and mu plus 2 sigma. We are going to calculate this. And we know that mu is 14. So minus 2 times this number plus 2 times this number. So this becomes 9.9. This becomes 18.1. What does it mean? Any number less than that, any number larger than that is considered unusual. Is number 7 anywhere in between? No. The methodology is 7 is not an element of this. Therefore, yes, it is unusual. This is from set theory, not an element of, I'm going to write this. This means not an element of. If you have it, this class looks like epsilon means an element of, this is not an element. So yes, it is unusual. Would it be unusual? Absolutely. Why is that? Because it's beyond the two numbers. It's less than 9.9 or larger than 18.1. Find the probability of a couple having at least one girl among three children. I'm going to look at a couple of methods. Method one, probability of at least one is one minus the probability of none. And it's important that we know we are assuming the probability of G, that means having a girl, equals probability of B having a boy equals 1/2, which is really not the case. It's slightly different than that. But we are going to assume that. So probability of none, that means all boys, probability of a boy is 1/2, all boys is to the uh, third power, because we are looking at three children. If it were 10 children, 1/2 to the power of that. So 1 minus probability of boys to the power of 3. And I'm writing this out. It's important to know if they were different. Let's say I'm making things up. Let's say probability of girl was zero 0.6, which makes probability of boys 0.4. So you would put 0.4 here. Okay. They happen to be equal. We don't want to mix them up. One more time. Over here, you put probability of boys. If they are different, you want to pay attention to that. And so 1 minus 1/2 to the third, this is 1/8. So we get 1 minus 1/8, or 7/8. Here's one method, you're done. End of the story. Second method, use binomial distribution. N is 3 because we are interested in among 3 children. Probability of a girl is the probability of success because at least one girl is 0.5. So again, if boys and girls have different probabilities, let's say this was a probability of girl was 0.6, you would use 0.6 here. So pay attention to P that you use here. X is larger than or equal to 1 because we want at least 1, right? Probability of at least 1. It happened that P equals Q. Okay, I want you to be careful with that. In this case, it is where X is 1, 2, 3, right? In other words, at least 1, we want X to be 1 and 2 and 3, and we add them up. So probability of 1 plus probability of 2 plus probability of 3. So we use the binomial distribution, which has this formula. And in this formula, N is 3. Again, P and Q happen to be the same. Okay. So both of them happen to be 0.5. So we plug in. So probability of X is 3 factorial over X factorial, 3 minus X factorial, 0.5 to the power of X, 0.5 to the power of 3 minus X. Again, if they had different probabilities, and let's say G, probability of G was 0.6, this would be 0.6, this would be 0.4, everybody, okay? I mentioned that because sometimes they do give you probabilities that are not the same. In fact, in reality, they are slightly different, so they're not 50% each. And so, again, I can plug in 1 and 2 and 3 and add them up. Or I can go with 1 minus probability of 0. I calculate probability of 0 here. So I replace the X with 0 and subtract it from 1. Again, note probability of B is 1 minus probability of G. Okay, for P of 0. This one, it's important to understand what we are saying here. This P and Q are the same in this case. They may not be. P for Binomial distribution is the probability of success, probability for girls, okay, versus Q, probability 1 minus that, probability of birth for boys. Distinguish between the two. So this is probability of G, this is probability of B. Again, they happen to be the same, but I want to make sure that we are clear. Now, probability of x larger than or equal to 1 ultimately becomes 1 minus this to become 1.5 to the third power, and obviously 0.875 or 7/8. Okay. However you look at it, you come up with the same answer, but my point is you really want to know what is P and what is Q, and don't mix them up. They happen to be the same. If an alarm clock has a 0.9 or 90% probability of working on any given morning, what is the probability that it will not work? This is complementary event. The probabilities must add up to 1. So probability of A naught is 1 minus probability of A. So probability of working is 0.9. Probability of not working, we put W bar, is 1 minus probability of working, which makes it 1 minus 0.9, which makes it 0.1 or 10%. What is the probability that two such alarm clocks will not work? This is called, in essence, quality control, okay? Making sure things are in order. That's why you could use two alarm clocks, for example, on the day of the exam. Probability of the first one working, W sub 1, probability of an alarm working. And of course, if you put a bar at top of it for it not working, the complementary event. So what is the probability that two such alarm clocks will not work? Probability of W1 bar intersection W2 bar, probability of the first and second alarm not working. Well, the two alarms are independent. The only way they become dependent if they are plugged in to the same outlet and somehow there's a power outage, then they become dependent. But generally speaking, they are independent. So probability of W1 bar times probability of W2 bar, each one has a probability of not working as a 0.1. So multiply the two and you get 0.01, which means if one alarm clock has a 10% chance of not working, which is terrible, two of them, the probability goes down to 1%. This is the concept of a probability control. So there is 1% probability that two such alarm clocks will not work. Okay. And that is used in important stuff, such as, for example, airplanes, making sure that the engines work independently. Okay. So if one fails, others won't, and so on. And so on and so forth. We're going to continue with the same question, part C. What is the probability of being awakened if you have two such alarm clocks? So we have from the previous page, probability of working one is 0.9, not working is 1 minus that, and for both of them to fail is 0.01. So obviously, probability of being awakened must be 1 minus probability of not being awakened. And we are assuming this is the probability that we won't, because this is the probability that both alarms fail. So 1 minus that is 0.99. The assumption is we do wake up to the alarm clock. Granted, some people may not. Second method is called the addition method. A union B is probability of A union B is probability of A plus probability of B minus probability of A intersection B. So probability of W1 union W2, that means working, because we are looking at waking up. So probability of W1 union W2 is probability of W1, 0.9, plus W2, probability of W2, which is also 0.9, minus the probability of W1 intersection W2, which is 0.9 times 0.9. And we get to the same answer, 0.99 or 99%. Now, please understand, we are looking at working. Working is 0.9, okay? Third method, we use binomial distribution when n is to y2 because there are two alarm clocks. What is the probability of success? Working, which means we wake up. So probability is 0.9. Here's the formula. We are going to plug in, replace the n, replace the p, and of course, q is 1 minus that of 0.1. So that's the binomial distribution. 2 factorial, p of x is 2 factorial over x factorial, 2 minus x factorial, 0.9 to the power of x times 0.1 to the power of 2 minus x. It's very important to write these things out. If you want to use a calculator, you want to show your work, because just what the calculator does is not good enough. Now, you want the probability of x larger than or equal to 1, because if one works is 2 is fine. If both of them work, that's fine. So that means probability of x equals 1 plus probability of x equals 2, which is easier to calculate, 1 minus probability of 0. So into this, because it's been put in, replace the x with 0, subtract it from 1. So into this, x is replaced by 0. Get 1 minus 0.01 or 0.99. There are 3 different ways to solve this. I hope you're okay with that. So one is that we already had the 0.01, you subtract from it. The other one is the addition method. And finally, the binomial distribution with n being 2 and p being 0.9 will do the job as well. During an NFL season, there were 256 games played with 1,307 touchdowns scored. And of course, we're going to use Poisson distribution. What was the mean number of touchdowns, I'm going to call it short, TD, scored in each game during the season, rounded to the nearest 0.0000014 decimals. So what's the Poisson distribution? Poisson distribution, the probability of the event occurring x times over an interval. The interval can be time, distance, area, volume, or some similar unit, is given by p of x equals mu to the power of x, e to the power of minus mu over x factorial. That's the formula for the Poisson distribution, where e is the base of a natural log, 2.71828, and it continues indefinitely. You want to use e rather than this number. Mu is the mean number of occurrences of the event in the interval. The parameters of Poisson distributions are mu and sigma. Sigma equals square root of mu. So the mean number of touchdowns would be the total number of touchdowns, 1307, over the number of games, 256. And we get this number, We're going to go with 4 decimals. So we put more than 4, 1, 2, 3, 4. Because this number is 6, everybody, we change the 4 to 5. So it's important to put this in an appropriate format, everybody. 4 decimals in this case. So let's write this. Let's replace the mu with this number. Again, when you do the actual calculation, you want to go with many, many, many decimals to get a better approximation. And again, I suggest you keep it as E. E is roughly 2.71828 and continues indefinitely. Okay. On January 10, 2010, the Green Bay Packers and Arizona Cardinals played a playoff game in which there were 13 touchdowns scored. What is the probability that a random game would have had that many or more touchdowns? Well, we want the probability of X larger than or equal to 13. That means probability of X equals 13, 14, 15, and it goes indefinitely. So it's easier to go with the complementary event. 1 minus the probability of X less than 12. Calculate this one, subtract it from 1. So that would be a faster way to come up with the answer, everybody. Okay, so what do? You can put it into your calculator. Poisson distribution, second variables, Poisson PDF, enter mu or lambda and X, enter or paste. If using Poisson CDF, it gives the sum of the probabilities from 0 to X. So we're going to put Poisson CDF. Lambda is this number. Okay, and again, as many decimals as possible. X value is 12. We are looking at calculating this piece, everybody. And 1 minus that is the answer. And again, we stopped here next to it is 0. So that's the rounding methodology, everybody. Okay, so as far as the number of decimals, you always want to pay attention to the way they ask you to do it. Okay. Practically, we are done. Let's look at the last part. So I want to fill up this column. I want to quickly go over what we need to do. The first column lists the number of touchdowns, TD, 0, 1, 2, 3, and so on and so forth. And again, this is filled in already. The second column is for the predicted probability. Again, we want to go with calculating probability of X equals 0, put it here, 1, put it here, and however many decimals. In this case, they're asking for 4 decimals. Okay. Okay, so the second column is the predicted probability that the game chosen at random will have that many touchdowns scored. Calculate these values, round them to the nearest 0.0001. The third column is for your best prediction about the number of games. So this is the number of games during the season that had that many touchdowns scored. Round these values to the closest whole number. Reminding everybody of what we did in the previous. Okay. And so we're going to start with 0. So this formula that we had, replace the X with 0. Or if you put it into a calculator, because this becomes 1, 0 factorial is 1, and it gives you or you can go with just e to that power or do it with the Poisson PDF in this case. When you write the formula here, you don't need the Poisson. And that gives you the answer. So you put the number here, this one. Okay. So this number, you put it here. Now, I didn't round it to 4 decimals, but for the sake of 4 decimals, 1, 2, 3, 4, this 0 changes to 1. I want you to know that. So I'm going to write it up here. I'm going to write with many decimals, specifically 4 decimals. I put it there so you can see that. Okay. Now, you have to multiply this by the number of games. So you're going to multiply the answer by 256. You get this number. And you have to round it to the nearest whole number, 1.55. So for 1.5, this number says you have to round it to 2. So that is this number. Now, we do the same thing for number 1, and we put it here. So into this formula, you are going to replace the x with 1. Okay, so we did that. And this number goes there. And now I'm going to pay attention to 4 decimals, 1, 2, 3, 4. Okay, so 9 next to it is 5, becomes 10, so 1, 0. I'm going to multiply this number by 256. I get 7.9 something, and I wanted a whole number, so it becomes 8, everybody. I'm going to go back to this or to this and change this value from 0 to 1 and now to 2. Okay, I get this number, and since I want 4 decimals, 0.07900, 0 next to it is 2, so it doesn't change. And then I multiply by 256 becomes this number, 20.23, rounded to the whole number is 20. So this is the number, and this is rounded to 20. And of course, you can continue, but that's the concept that they're asking.